Myself, Dr. K. Viswanath, Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Dundigal, Hyderabad. In this session, we are going to study problems of a deflection and slope of a simply supported beam with an eccentric load, and deriving the formulae for the case of deflection of a simply supported beam with uniformly distributed load. Now here, the derived formula for simply supported beam with an eccentric point load, the deflection for that type of beam, that is the eccentric load of a beam is the eccentric load. Eccentric load means not at the center of the beam. It is away from the center, either leftward towards left or towards right. It is distance from A here and distance from B. The span of the beam is L. So here the W. The deflection at point C is for an eccentric load of a simply supported beam by using double integration method is W A square B square by 3I times L, 3IL. Here W is the weight which is acting eccentric load, where A is the distance from left support, B is the distance from the eccentric load, point of action of eccentric load from right side direction, right support, and E modulus of velocity, I moment of inertia, that is second moment of area, where L is the span of the beam. Okay, this is the span of the beam. That is the deflection. So what about slope? So if you want maximum deflection, this is the formula for derived formula for maximum deflection is WB by 9 times root 3 EI times L times A square plus 2AB power 3 by 2. And one more thing very important is that the slope we have derived. What is the slope? The slope at point A is theta A is minus negative times WAB by 6EIL times A plus 2B. So these are formula derived. Now, how to apply those formula in solving the problems? Consider the problem, that is slope at the left support. Determine the slope at the left support, and deflection under the load. Deflection under the load, and maximum deflection of a simply supported beam. Maximum deflection of a simply supported beam of length, where L is the span of the beam, span between two supports. There is 5 meters, which is carrying a point load of 5 kilonewtons. A point load of 5 kilonewtons. The eccentric load is 5 kilonewtons, that is converted into newtons, that is 5 times 1000, that is 5000 newtons. At a distance of 3 meters from left hand, that is A. And L minus A, B equal to L minus A, that is 5 minus 3, that is 2 meters left support, that is 2000, that is 2 meters, that is 2000 millimeters. So in pictorial presentation, this is W, that is how much, 5 kilonewtons, convert into newtons, 5000, left support 3 meters, 3000 millimeters, from right support 2000 millimeters, and the span is 5000 millimeters. This is A and it is B and C. So it comes under the case of eccentric load. So we need what to determine? We know the material property. The modulus of velocity is 2 into 10 power 5 Newton per square millimeter, and moment of inertia, that is second moment of area, that is 1 into 10 power 8 millimeter per 4. So theta A we want, that is slope at the left support, that is theta A, slope at the left support, and deflection under the load, this is the point C, that is YC. Next, and also maximum deflection of a simply supported beam of length 5 meters. What is the maximum deflection? Why maximum? These are the 3 objectives we have to calculate. So first objective is, we know the slope at the left support theta A, that is, this is the formula. Substitute directly. That's it. We'll get it if you know the formula. Now, W times AB by 6EIL times A plus 2B. What is A value? A value is 3000 millimeters. B value 2000 millimeters. W value 5000 newtons. 6EIL, 6E, where E is modulus of velocity 2 into 10 power 5 Newton per square millimeter. I value, that is 1 into 10 power 8 millimeter per 4. L value 5000 millimeters times A, that is 3000. 2B, 2 times B, 2 into 2000. So the value of slope comes in the form of, in the units of radians. After calculation, then the derived value is, the calculated value is negative of 0.00035 radians, that is theta A. Okay, this is the radians. Okay, if you want in degrees converted with, okay, with the conversion factor, then it comes into the degrees. Now, that is objective 1. Now, what is that here? Negative sign value of slope indicates that the angle made by the tangent A in which direction? Anti-clockwise direction. Now, the second objective is the deflection under the load is given by the deflection, that is WYC at C W A square B square by 3EI times L. Substitute W value, all known values. We know W, that is 5000 newtons, A, B, E, I and L. Then the calculated deflection, the deflection at the point at the concentrated load or eccentric load action, where it is the point C, that YC is 0.6 millimeters. Now the next third object is the maximum deflection. What is the maximum deflection formula? That is YC, Y maximum is WB by 9 times root 3 EIL times A square plus 2AB power 3 by 2. That is, substitute W 5000 newtons, B value 2000 millimeters, 9 times root 3, E value 2 into 10 power 5 Newton per square millimeter, I value, this is I value, it is E value and it is L, it is W, it is B. Okay. So WB by 9 root 3 times EIL. Next A, this is A square times 2A and it is B power 3 by 2. After calculating, after substitution and calculating, the value of the maximum deflection value is observed as 0.6173 millimeters. So what is the maximum? How much it is maximum in comparison to the where the point load, the deflection under the load, that is 0.0173 is value millimeter is more than the deflection. So Y maximum is YC plus 0.0173. So the difference between maximum deflection and the deflection under the load is 0.0173 millimeters. This is the deflection difference. But the maximum deflection value is 0.6173 millimeters and the deflection under the load value is 0.6 millimeters. So it's a very simple. Once you remember and understand the derivation, how derived formula, then just substitution, the known values and unknown value how to. The unknown values are output parameters, the known values are input parameters. And in between unknown and known, how do we get it? By using the derived formula. The derived formula here observed as the slope at the left support is negative of WAB by 6EI times L A plus 2B. And it is theta B, that is the deflection under the load is YC equal to WA square B square by 3I times L. And the maximum deflection value, that is Y maximum equal to WB by 9 times root 3 IL A square plus 2AB times 2AB power 3 by 2. Okay, now coming to the case of deflection of a simply supported beam with uniformly distributed load. Okay, with uniformly distributed load. So far we have studied two cases by using double integration method. What is the case 1? The case 1 is that deflection of a simply supported beam having a concentrated load at the center of the beam, and both the deflection slope are calculated. Now, this is the case 1. Case 2. What is the case 2? The case 2 we have studied by using double integration method. An eccentric load, the support, simply supported beam having eccentric load, it is L by 2 here, but the first case L by 2 center load here, whereas here it is A from left support and B from right support and length. Now case 3, here deflection of a simply supported beam with uniformly distributed load. What is that meaning here? The simply supported beam with the uniformly distributed load. This case we are going to do it. We are going to study what is the slope and what is the deflection. So here we considered a simply supported beam AB of length capital L and carrying a uniformly distributed load of W, that is small w per unit per W newtons per unit length over the length throughout. So the reactions at A and B. So we have to calculate the reactions at point A and support A and support B by using the concepts of a shear force and bending moment diagrams. By using sign conventions and by using sign conventions of bending moment and also sign conventions of shear force, we have to calculate the reactions at point A and point B. So after applying the reactions observed here, equal reactions at support A and support B as WL by 2 and WL by 2. That is the reaction. Here small, this W is not the point load, it is a uniformly distributed load. So WL times by 2 here, equal reactions. Now what to do? We have to consider the moment, bending moment equation at a certain section, that is at a distance x from left support. That is what we are following. We can also take, we can also calculate bending moment of a section from right support also at a distance x. But we are following for case 1, case 2 and case 3. So we are used to, so that we are using here at a support from left support section x at a distance small x from A. Now the bending moment at the section x is mx equal to what will happen, the positive bending moment sagging position, that is RA times x, negative minus, here this portion there is UL is there, W into capital W into x times x by 2 in negative direction. So that is what we substituted here, that is mx equal to WL by 2 times x minus WX square by 2, mx equation. Now we know the bending moment at any section also given by another equation, that is m equal to EI times d square y by dx square. M equal to EI times d square y by dx square. Now this is also equation, that is bending moment at any section, and before also derived that bending moment at any section. So both equation 1 and equation 2 we are going to equal it here. Then that is EI times d square y by dx square equal to WL x by 2 minus WX square by 2. This is the generic equation. If by using double integration method, if we integrate once this equation, that is dy by dx, slope equation can be observed. And one more thing, and integrating again that slope equation once, then we can see or we can observe the deflection equation. That's what we have done here. Here integrating the above equation once, first integration, that EI times dy by dx equal to WL by 2 times x square by 2 minus W by 2 x cube by 3 plus C1. The C1 is called as constant of integration. This constant of integration can be obtained by using boundary conditions. Yes. Now again integrating the above equation, that is equation 1. What we get it? We'll get deflection equation. But there, if in a deflection equation, there are two constants of integrations, that is C1 and C2. So this C1 and C2 can be obtained by applying two boundary conditions. So let us calculate the constant of integrations. After calculating the constant of integration, these constants C1 and C2, and substitute back in equation 1 and 2, we'll get it the slope and deflection equations of a simply supported beam by using double integration method. Why it is known as double integration method? Because we are integrating twice the original equation, that is A times d square y by dx square equal to w by 2 times x minus wx square by 2. Now let us find what are the two boundary conditions are. The two boundary conditions are at x equal to 0, y equal to 0, and second boundary condition is that x equal to L and y equal to 0. Substitute these two conditions in above equations, two boundary conditions, two equations and two unknowns, we will get it. So it is compatible equations. So at x equal to 0 and y equal to 0, substitute these things in equation 2. Then we will get it C2, that C2 equal to 0. Substitute back this C2 in the equation 2. And what about C1? Substituting the second boundary condition, that is at x equal to L, y equal to 0. That is in equation 2. Again we get what is the C1 value. The C1 value observed here, it is WL3 minus WL3 by 12 plus WL3 by 24, then minus that after doing simplification and doing LCM, taking LCM, there is minus negative WL3 by 24, that is C1. Substitute C1 and C2 in equation 1 and 2, we will get, we can observe here the equation of a slope and also the equation of a deflection. This is the equation of deflection, equation 4, and equation 3 is slope equation. The slope equation for this case here, it is observed as I times dy by dx equal to WL by 4 times x square minus w by 6 times x cube minus w by 24 times L cube. Now, wherever x varies, if I substitute x equal to 0, at 0 distance, what is the slope? If x equal to L by 2, what is the distance? We will calculate at that position at a distance of. So this here, the slope equation here, it is proportional to the distance. X depends upon x value. Now the deflection equation, after substituting C1 and C2 in above equations, okay, the deflection equation is calculated as I times y equal to WL by 12 times x cube minus w by 24 x power 4 minus WL cube by 24 times x. Now here the equation 3 is known as the slope equation. This is the slope equation. And another equation, equation 4, is known as a deflection equation. This is the deflection equation. So we can find the deflection, that is the value of y, at any point on the beam by substituting different values of x. Different values of x in the equation 4. And the slope, in the slope equation, we can find the slope of the beam at a distance of, at a different values of x, at different values of x, the slope can be calculated. Okay, now we want, now these are the equation, now we want where we want slope at the supports or slope at the different where x is varying. So if you want a slope at the supports, slope at the supports, that means dy by dx at A. Slope at support B, dy by dx at B. Now slope at support A comes, that is theta A. and slope at support B, that is theta B. So at x equal to 0, in the substitute in the slope equation where x equal to 0. What is the slope equation derived here? The slope equation is WEI times dy by dx equal to WL by 4 times x square minus W by 6, x cube minus WL cube by 24. In that x equal to 0 is substitute. Then what will happen here? The slope at A, theta A equal to minus WL cube by 24, that is 1 by times EI. That is WL cube by 24 times EI. That's what we can see it. WL cube by 24 EI. So here, this is the small w and it is capital W. Now here, what is the W small w? The small w, what will happen? Small w times L. That is nothing but the total load capital W. Here, small w indicates the uniformly distributed load, whereas capital W indicates the total load. So this small WL cube by 24 is converted into total load, that is capital WL square by 24 times EI, that is the slope. So what does that negative sign means? The tangent at A makes at an angle with AB. Tangent at A makes an angle with AB in anti-clockwise direction. Okay, how it is making in angle in anti-clockwise direction, theta A. That's why it is WL square by 24 EI, where capital W is the total load, L is the span of the beam, E is the moment of inertia, E is modulus of velocity, and I value is moment of inertia. Yes, second moment of area. Let me again explain. What are the units? The units for W is newtons, where L is in millimeters or in meters, or newtons or kilonewtons. Now here, you follow here millimeters. Now E, Newton modulus of velocity, that is Newton per square millimeter, where I is millimeter per 4. Alright. Now this is the slope. The units of radian, the units of slope is radians. Theta A and theta B is same because it is symmetry about y-axis, vertical axis. So theta A and theta B. The slope at support, left support, and the slope, the value of the slope at right support, both are equal. Why? Because the total load is uniformly distributed load. It is symmetrically acting equally. The reactions are same. That is WL by 2 and WL by 2. Same reactions. And also it is symmetrical about axis Y. That's why here the slope is remains same. That is WL square by 24 times EI. Slope at the supports. Now we calculated slope at the supports A and B. We will need maximum deflection. Where it will happen maximum deflection? At the center. Where the point C, that is the maximum deflection at the center of the beam. That is where x equal to L by 2. Substitute x equal to L by 2 in the deflection equation. The deflection equation here it is WL by 12 times x cube. Here EI into Y equal to WL time L by 2 WL by 12 times x cube minus W by 24 x power 4 minus WL cube by 24 times x. Okay. This is the equation, L cube by 24 times x. Now, one thing you can do it, this formula also can be changed here itself. Yes, one thing. Yes, we'll make it substitute. Okay, substitute in this equation x equal to L by 2. Now substituted here x equal to L by 2, W L by 12, small letters, L by 2 times whole cube minus W by 24 times x power 4, that is L by 2 times power 4, minus W L cube by 24 times x, that is L by 2. Now simplify it, WL into L cube, that is L power 4. This is 2 cube, that is means 8. 8 times 12 times 8, that is 96, minus WL power 4 by 2 power 4. What is the 2 power 4 value? 2 times 8, 8 into 2, 16. 16 times 24, that is 384. Minus WL power 4 by 24 times 2, that is 48. This value, if you simplify it, it comes as 5WL power 4 by 384. This 5WL power 4 by 384 value, that is EI times YC. So YC equal to minus 5WL power 4 by 384 EI. This is the formula in terms of UDL, uniformly distributed load, minus converted to total load WL into L cube by 384 EI. Now in terms of total load, minus 5 times W times L, small w, uniformly distributed load times total span, that is total load, capital W, L cube by 384 times EI. This is the value. Minus 5 by 384 WL cube by EI. Now, this is the negative indicates what? What is the negative deflection value? YC equal to minus 5 WL cube by 384 times EI. This negative sign indicates the downward direction. Deflection is taking place in the downward. So, that is the downward deflection. When the UDL is acting, the deflection is in downward direction. The maximum deflection is taking place at the center, point C. There is a point A and a point B. So 5 times WL cube by 384 times EI. Okay. Now, how to apply this derived formula in solving the problems? Let us consider, take one problem. Take problems and we'll try to solve. We'll try to apply those formulae. A beam of uniformly rectangular section 2000 millimeters wide and 300 millimeters deep is simply supported at its ends. It is a rectangular section beam and it carries a uniformly distributed load of how much? 9 kilonewton per meter. 9 kilonewton per meter. Okay. Next, run over the entire span of 5 meters. If the value of E, of the beam material is 1 into 10 power 4 Newton per square millimeter, find the maximum deflection and the slope at the supports. So in graphic presentation diagram, in a figure presentation, the UDL supports A and B. Okay, alright. What is the E here? That is 9 kilonewton per meter. What is the span of the beam? The span of the beam is entire span. The span is 5 meters. Alright. Yes. Yes. Modulus of velocity. E value is given. E equal to 10 power 4 Newton per square millimeter. What about I value? I comes from BD cube by 12. That is not given here. So BD cube by 12. Derive, that is 200 into 300 cube by 12. I value we got to know it. Now 9 kilonewton per meter. Either we have to follow 9 Newton per millimeter or 9 newtons per meter. If we convert into Newton per millimeters, that is 9 Newton per millimeter. The W is 9000, yes, 9 Newton per millimeters only. Now, what is the total deflection? W times L. So, 9 Newton per millimeters converted into, what is the total deflection? Small w times L. So, L, what is the span? That is 5 meters. That means 5000 millimeters. L equal to 5000 millimeters. So, 9 Newton per millimeter times 5000 millimeters. That is 45,000 newtons W. This is what? W. E value we know, calculated. I equal to BDQ by 12 from the concepts of second moment of area. That is 4.5 times 10 power 8 millimeter per 4. So now here E equal to 1 into 10 power 4 Newton per square millimeter. Now calculate theta A and YC. What is theta A value? What is the theta A formula? The theta A equation is negative of W L square by 24 times EI. What is this is the total load. Even though uniformly distributed load, that uniformly distributed load is converted into total load. That derived formula is negative of negative W L square by 24 times EI. This negative W is 45,000, L is 5000 millimeters. 24 E value 1 into 10 power 4, I value 4.5 into 10 power 8 millimeter per 4. This is in newtons. It is in millimeters square. 24 EI Newton per square millimeter. I millimeter per 4. Now this theta A is 0.0104 radians. So here it is symmetrical. That's why theta A that is equal to theta B. Such way theta B equal to theta A. The value of the slope at supports is 0.0104 radians. Now what is the equation next? The deflection equation. The deflection at the center, that is 5 times. This is the negative value. Negative of 5 times WL cube by 384 times EI. Substitute known values. W we know known, L known, E known, I known. Those values we substitute, then the YC. The YC equal to 16.27 millimeters. Okay. That is the derived here. That is YC equal to 16.27 millimeters. The deflection. The huge deflection. That is 16.27. Visible deflection we can see here in this problem. The next problem, we can see it here. A beam of length 5 meters and of uniform rectangular section is simply supported at its ends. Okay. At its ends, it carries a uniformly a beam of length. It is again 5 meters and having a uniform rectangular section is simply supported at its ends. It carries a uniformly distributed load, that is again 9 kilonewtons per meter, run over the length. Calculate the width and depth of the beam if permissible bending stress is 7 Newton per square millimeter and central deflection is not to exceed 1 centimeter, that is 10 millimeters. So what is the value here? 9 kilonewton per meter, simply supported, and span, that is 5 meters. Here permissible bending stress is 7 Newton per square millimeter, and also maximum bending stress not to exceed. One more value given, that is E value, that is modulus of elasticity of a material, that is 1 into 10 power 4 Newton per square millimeter. Now let us begin. We want, what are the objectives? We have to calculate the width and the depth of the beam. What is the cross section of the beam we need? That means I value. If we know the I value is given, no. That I value, then we can know it, BDQ by 12. Now, but one hint is that deflection. This is the hint, input given. So what is the YC? That is 5 times WL power 4 by L square by L cube by 384 times EI. 5 WL cube by 384 times EI. We know the value of the YC. Total load, we have to convert in total load 9 kilonewton per meter times 5 meters, 45,000 W. L 5,000 millimeters, 380 for E value 1 into 10 power 4. I value is known. Calculate I value. After knowing I value, B into D cube by 12. So in that one has to know what is the B value. This one equation, from this I will come. The next equation, slope. What is the slope equation? There also. And we know the hint of bending stress. With the help of bending stress, we will calculate the length and width. Okay, begin. Start. Total load W equal to W times small w, uniformly distributed load times span of the beam, that is 45,000 newtons. Bending stress sigma is 7 newton per square millimeters. YC, that is 1 centimeter, that is 10 millimeters. The value of the E 1 into 10 power 4 newton per square millimeter. Width of the beam B, depth of the beam in millimeters. I equal to BD cube by 12. We know the value of the YC, from that calculate I or BD cube. The BD cube is calculated as, after substituting the known and unknown, substituting the unknown values, that is W, L, E and 5 times 384, calculate multiplying the factor, then BD cube equal to 878.906 into 10 power 7 millimeter per 4. Now, we know the maximum bending moment for a simply supported beam carrying a uniformly distributed load, that is calculated as, we know that is WL by 8, where W here it is total load. That is M equal to, we got to know the value, that is 281.2500 Newton millimeter. Now, the pure bending equation we know, M over I equal to sigma by Y equal to E by R. Based on the given data, we got to know the relation to be used as M by I equal to sigma by Y. What is the M value? That is 281.2500 M by I. What is the I? BD cube. Here another BD cube is going to come. Okay, that is the BD cube by 12, 7 by Y equal to D by 2. Now, after simplifying, BD square equal to, what is the value here? 24107.142.85 millimeter cube. Here it is BD cube, here it is BD square. Now, dividing equation 1 by equation 2, that is BD cube by BD square, then what will happen? BB get cancelled, D, then depth value comes. So equate, divided by equation BD cube, equation 1 BD cube, and another one is the BD square, this is the BD square. Divide by that equation 1 by equation 2, then the value of depth is observed. Substitute this depth value in one of the equation, either equation 1 or equation 2, then we'll get the width of the beam. So the width of the beam is observed here, that is 181.36 millimeter, and the depth of the beam is observed as 364.58 millimeters. Alright. So the novelty of this problem in this section is that given here the deflection, maximum deflection was given. So if we use this cross section of the beam, the cross section of the beam gives what? The value of I, that is the moment of inertia, second moment of area. So at this geometry and moment of inertia calculated, but deflection can be known. The deflection, if we substitute these values, that is 10 millimeters will be obtained for this. So if you want a deflection, suppose very important design characteristics, we can use this problem for calculating. If you want to minimize the deflection, if you want 2 millimeters deflection, let us use a 2 millimeters deflection, then you can know the geometry of the beam. If you want 1 millimeter deflection, we can know what should be the geometry, what is the depth and width of the beam, cross section of, especially rectangular cross section. Now these are the references, textbooks are followed in this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.